Hi everyone, this is a screencast about linearizing graphs, a very common technique in physics. Straight line graphs are really useful, and if we have things that aren't straight, oftentimes we want to straighten them out. So what I've got here is a linear graph. So I'll just go ahead and draw a line on here. So we know this looks like it goes probably somewhere around there. Okay, so that's the line that we could draw from that. Okay, now in math class you want to find the slope, but you usually don't do much with it after that. But in this class, the slope can be really useful. So what we're pretending here is that we know that the formula here is y is equal to the square root of some constant a times x. So what we really want to know, if you think about it, is we can use the slope to figure out what that constant a is. Okay, so in this case I just have y and x, so I need to find the slope, so we'll just go ahead and do that manually. So I know the slope, change in y over change in x, so I'm going to use this point, which is 10 and 20. Now you need to make sure anytime you do this that you use points that are on the line that you drew. So for example, on the AP exam, this is very common for you to have to draw a graph, and then you draw your best fit line and you find the slope of that line. So I can use 10, 20. It's a data point, but it's on the line. If we look at this data point here, that is not on the line, so I can't use that to find the slope. I also can pick a line, a point on the line that's not a data point, and that's fine as long as it's on the line. So I'm looking at this going, you know, that point looks like it's about 0, and let's say that's 1.5. Okay, so now I can find the slope, change in y over change in x. So I've got 20 minus 1.5 over 10 minus 0. So it looks like I've got about 18.5 over 10. So the slope is equal to 1.85. Okay, so if I'm writing this equation in terms of y and x, our point slope form is y equals mx plus b. And so y is equal to 1.85, and in this case the intercept, I've picked that out as about 1.5. Sorry, that is 1.85x. Let's see if I can get my eraser here. There we go. So that's 1.85x plus 1.5. Now I'm going back and I'm looking at this up here, and I know that y is equal to the square root of a times x, and I should probably put in there some sort of constant plus b or something like that. But the idea here is just by comparison. So I know that the coefficient of x in this equation is 1.85, and I see the coefficient of x in this equation is square root of a. That means that I can say that the square root of a is equal to 1.85. So that means a is equal to 1.85 squared, which is 3.42. So this is a tool that we use a lot in our class. The slope of the line has some sort of meaning in terms of the physical quantities that we are graphing, and so we're trying to come up with some sort of constant. So let me give you a more specific example of that. Okay, so here we have some distance and time data, and it is clearly not linear. And so what we want to do is we want to linearize this, okay? Because if we can get it into a straight line graph, then we can use the slope to help us calculate something that we want. So first of all, the first step in linearizing is to figure out what shape you have. Okay, and the shape of this graph, if we look at it, it's not real sharp, but I believe that's a parabola. And we know a parabola is always proportional to y is proportional to x squared. Or you can think of it as y is equal to some constant times x squared plus some other constant times x plus another constant. Okay? And so what we want to do is we want to linearize this. Okay? So if you look at it, right now we have distance versus time. If we graph distance versus time squared, then that'll help us solve this problem here. Okay? So I'm going to go here, and our distances, actually when we go to the next page it went 0 through 5, so I want to make this t squared. So to make a long story short, if you're linearizing a parabola, you want the x value to be what was on the x-axis squared. And then we've got distance there in meters. And so first t was 0, the first one was 1, the second one was 2, so when we square that we get 4, and then 9, and then 4 squared is 16, and then 25. We're going to keep the distance column the same, so I'm going to flip back and forth here a little bit. So we've got 12, 14, and 25. And then we've got 40, 59, and 84. So we've got 40, 59, and 84. And now we make a graph of distance, and you'll notice I'm labeling the axis with the variable symbol and also in parentheses the units that it was measured in. That's good graphing procedure. You always want to do that. Okay, we almost always want to start our graphs at 0. And so now we've got to set the scale so that we get this up to 25. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So a good scale, depending on how to do that, I guess we could go by 2.5. So we could say this is 5, 10, 15, 20, and 25. And then our distance has to go up to the same scale that we had before. Let me just peek at what I did earlier. So I went by 15s. So we'll do that again here. So we've got 15, 30, 45, 60, 75, 80. Excuse me, 90 there. Okay, and now we're going to plot this, and if we did things right, we're going to see that the data is relative as a straight line. That's the whole point of doing this. So 0, 12, 1, 14. So 1 is going to be really close there, so it's going to be like that. We've got 4 and 25, which is going to be kind of up here. We've got 9 and 40 out there. We've got 16 and 59 about there, and then we've got 25 and 84. So 75, 84 would be about in the middle there. And you can see that looks pretty linear. And so if we look at that, let's draw the line through there. So best fit line, remember, it does not have to go through every single data point. You want it to kind of go through the middle of the data. If you have some, I probably could have moved that one line a little bit. Oh, and I just missed that point altogether. Yeah, that would help. Okay, so when I say I missed that point, this point I put in the wrong spot. So graphing the points properly is always helpful. So that makes it look a little better. So I probably could have brought, in terms of a best fit line, I don't think I can change that. I probably should have brought this end up a little bit. So you should have all the points nearly on the line, about the same, on either side, and so on. Okay, let me get rid of these stray marks here. All right, so now we want to write the equation of the linear graph. So we want to go ahead and take the find the slope of the line. And so to find the slope, I need to pick 2 points. And here's a good example of, if I pick this point, it's not a data point, but it's right there at an intersection on the grid. That's always helpful. So that would be 2.5 and 15. So that's one of my points. And let's say I use another one. What's good there? So maybe this one on this end. That's pretty close to the grid, so maybe that is 25. And the data point says 84, but it looks a little closer to maybe I'll just say that's like 87 or something like that. So the points on this, since my data point's not on the line, I probably shouldn't use 84 on there. Okay, so our slope, m, is equal to 87 minus 15 over 25 minus 2.5. And I'm going to hit pause and do that calculation and then start again. So if I can remember where to find the pause button. There we go. Okay, so I got a slope of 3.2. We have an intercept of, looks like it's somewhere around a little below 12, maybe 10. So the equation for this line is y is equal to 3.2 x plus 10. Now what I want to do next is I want to change that from y and x to the variables that we actually put on here. This is time squared, which is really important. So on the y-axis, I want to put the variable name that we had on the y-axis. So in this case, that's distance. So we're going to have 3.2 times time squared plus 10. Okay? And so the general relationship of the equation, we know that the coefficient in front of the time squared is equal to 1/2 the acceleration. Okay, so basically what we're doing is we're just making a comparison. So the coefficient of the t squared equation, or the coefficient of t squared, is 3.2 here, and in this equation we see that the coefficient of t squared is 1/2 a. So this lets us make the equation, so 1/2 a is equal to 3.2. So that's just a quick comparison. Excuse me. So that means a is equal to 6.4. Okay, and I'll let you fill in the units later. Since it's acceleration, it would be meters per second squared. Okay, so that's the idea. There are two other shapes of graphs that we typically see that we want to linearize. One is an inverse graph. So if we have y versus x and it's inverse, what that means is you have one of these things. So classic example from chemistry is Boyle's law, PV. P1V1 equals P2V2. In other words, what that means is that the y-axis is equal to some constant times 1 over x. Okay, and so to linearize that, so we're going to graph y versus 1 over x to linearize. Okay, so if you take all the x data, you have your x and y data. If we take y and we graph it as 1 over x, then you should get a straight line. Okay, and then the square root function. A square root function looks like this. So it gradually goes up like that. Okay, so that means y is equal to some constant k times the square root of x. So that's times the square root of x. So to linearize, what we're going to do is we're going to graph y versus the square root of x to linearize. So you're going to take all the x values in your table and take the square root of them. So basically you're going to make a new table. Okay, and if you graph y versus the square root of x, you get something like that. So the point here on our pendulum lab, what I want you to do is to graph the three. You're going to graph period versus length, you're going to graph period versus mass, and you're going to graph period versus the angle, the release angle. And so with each one, if it's not linear, then I want you to linearize it. Okay? So you need to identify what shape you have and go through that process. And you can go ahead and do that if you look on Pivot. You can make that graph by you can make a new column in the data. You can add a new column to the data. You can have it calculate whatever it is you need to calculate, like 1 over x or x squared or square root of x, or you can just do it on your calculator and make a new column and then change that graph. And after you linearize it, I want you to go ahead and make the straight line graph and show the slope. Okay, so hopefully that'll allow you to complete the data, make the graphs, and then linearize it. All right, I think that's all we need to do today.